Okay, so in this video, we will talk about another type of comparing two means. This is what we call paired observations. So we have an example. It will be more clear when we look at the example. So there are two tires of brands. So there are two brands of tires, sorry. So let's say this is, for example, this is Lassa. I don't know. Let's say this is Lassa. This is Bridgestone. Okay, Bridgestone. Okay. So these are two types of brands. So what they do is they just assign randomly to the left and right real wheels of 8 taxis, and the following distances in kilometers are recorded. Okay. So this is taxi one. This is brand A and brand B. As you see, Brande was able to be used for 34.4 thousand kilometers, and Brandby was used for 36,700 kilometers. And this is the second taxi. So now Brande is 45,000, almost 45,000, and Brandby is almost 47,000, and so on and so forth. Okay? So each taxi has two brands randomly assigned to the rear wheels, left or right. We don't know which one is left and which one is right. And I just want to test whether, let's say, whether mu A is equal to, first, this is the first thing, whether mu A is equal to mu B or not. Okay, so let's clear this. So whether the average lifetime of brand A is equal to the average lifetime of brand B. Okay. So that's nice. So what we can do is, well, compare two means. Okay, I don't know sigmas. So we don't know sigmas. Okay, we don't know sigmas. So what can I do is, well, assume sigmas are not equal to each other. Okay, so assume sigma 1 is not equal to sigma 2, and so on and so forth. Just continue like this. But if you just check here, okay, if you just check here, so just look at here. For example, look at the fourth taxi and look at the fifth one. Okay. So the brand A in taxi 4 is 32,000, and this one is how much? 16,000. Uh, so the kilometers elapsed in taxi 5 using the same brand is 16,000 greater than when you compare with taxi 4. Similarly, again, so for brand B, there is almost what? 60.7 thousand kilometers difference between these two taxis. So if you just look at this, well, there is not only a difference of brand A and brand B, okay, in this test, let's say, in this comparison. There is also an effect of the taxi drivers, okay? So probably this driver is a guy just like me at 40 years old, has two kids, driving very slowly, going to somewhere very slowly, very carefully, and so on and so forth. So that, well, he was able to make very high kilometers using brand A and brand B. But this guy is probably has just, uh, let's say, has just been eligible to enter university. Well, so his or her father, he just bought a new car, brand new car, as a gift for just being eligible to be able to get his or her education in a university. So he or she is very fast. So these are the numbers, okay? These are the kilometers. These are the kilometers that he or she make using his or her car, okay? So this is a young guy, very fast and furious, and this is an, let's say old, but middle-aged guy like me. So as you can see, there is a difference, not in the brands, but there's a difference between the taxis as well, okay? So just making something like this, so what I mean like this, just, I don't know sigma, assume sigma 1 is not equal to sigma 2, just compare x1 minus x2 bar minus mu 1 minus mu 2. That's not true, okay? Because, well, as I said, there is not only effect, there is not, uh, the effect is not only due to the brands, the drivers has also an effect as well. So what I should do is I should just uh, eliminate the effect of the drivers. Okay, how? So if I just subtract this one, okay, let's say this one from this one or vice versa, then what I will do is I will just, so for example, if you just subtract, let's say this one from here, what is the result? It's 2.3 thousand. If you just subtract this one, it is 1.3 thousand. Here it's just 1,000 and so on and so forth. So as you see, so for example, just look at this one. This is 0.9, okay? And this is what? This is minus, even minus. So this is minus 600, okay, 0.6. So as you see, if you just subtract brand A from brand B for the same taxi driver, you eliminate the effect of each driver, okay? So this is what we mean by paired observations. So this is a good, another good example is that, for example, you assume that, well, you just apply a diet, okay, a diet to 30 many guys. And what you want to check is whether people significantly lose weight. So, for example, if there's a guy here, let's say this is the first one, this is the first guy. Let's say this is the guy 1, 2, 3. So, if the initial weight is, for example, let's say 65 kilograms, okay. So this is, let's say, before the diet, and this is the after the diet. Okay? So let's say it's just he just loses 3 kilos. But if another guy is 130 kilograms, so what you expect this guy is to lose more than 2 kilograms. Okay, so it should be something like 9 or 10 kilograms. So let's say it's after the diet, so that's equal to 10 kilograms. So as you see here, before and after, the amount of lose weight just depends on the individual as well. Just like the amount of kilometers that you make using a particular brand depends on the usage of a driver. So so what I do is you just take the differences here, okay? 34.4 minus 36.700, 35.5 minus 46.8, and so on and so forth, okay? And let d bar is the, in fact, so after you just take the differences, you have x1, x2. If for our particular example, we have 8 many axis here, which let me show by D1, D2, D8. So the average of this one is D bar, okay? And the standard deviation of them is S bar D, okay? So let D bar and ST are mean and standard deviation of difference of n random pairs of measurements. Then, okay, so this is something we know. This is just like X bar minus mu divided by S divided by root n, right? So this is D bar minus mu D divided by st over root n. So this is the t-random variable with n minus 1 degrees of freedom. So how do we proceed with the hypothesis? Well, the hypothesis is mu1 minus mu2. So the difference of two mu's is equal to some mu d. So this is either, it can be 0, 2, for our example, it can be minus 3, and so on and so forth. So the test statistic is simply d bar minus mu d, okay, divided by st over root n with n minus 1 degrees of freedom. And this is our what? This is our critical region, okay? Ti forward to Ti forward with n minus 1 degrees of freedom. Then we calculate T observed. How? Well, so you just calculate the average of the differences, right? Minus mu d. Mu d just comes from the hypothesis here. And you can just calculate ST and divide it by root 10, which is the number of observations. And then if T observed is in the critical region, then you just reject the null hypothesis. Otherwise, you don't reject this. Okay. Um, so, okay, okay. So So for our particular example, okay, so this is brand A, brand B, and this is the difference of the first taxi, okay? 34,400 minus 36,700. That's equal to minus 2,300. So now what I do is I just take the differences of 8 observations. And now the problem becomes making a hypothesis test over a single mean, okay? Over a single mean. So what I do is first I will find the average of them, X bar, and then I will find the sample standard deviation. So I will call X bar as D bar, since, well, it's the average of the differences. I will use a different notation, but the whole process is the same, okay? So it turns out that the D bar, the average is 1,000, okay, so that's probably a minus. Sorry for this. Probably that's a minus. Okay, so this is probably a minus here. ST is equal to 1,454. Okay, so step one is check whether mu1 minus mu2 is equal to 0 or it's not equal to 0. So this is 0, right? And step two is, so this is a t-random variable with 7 degrees of freedom. So using alpha equal to 0.01, which means alpha over 2 is 0.005. So just look at the table. It turns out that, well, the rejection region is R minus this almost minus 3.5 and 3.5. So what is T observed? Again, so this is a minus, okay? Sorry for this. This is minus, this is minus 1,113 minus 0. Okay, so just give me a second. So this is equal to, okay, and let me just change this. This is 0, and so here I have a minus there. So it turns out that, well, this is minus 2.16, this is T observed. Just check whether T observed is in this interval, okay, in this interval. Well, is it here? No. So we don't reject the hypothesis. What does it mean we don't reject the hypothesis? At alpha level, significance level of 0.01, you cannot say that mu1 is different than mu2. You cannot say this, okay? So you cannot reject the hypothesis that, well, both brands have the same lifetime in terms of kilometers, okay? Now, the confidence interval is very similar to that one. So recall the confidence interval for single mean, it was mu smaller than x bar plus t alpha over 2 times sigma over root 10. So it's, no, sorry, s over root 10, right? S over root 10. It's the same thing. T bar x bar, t alpha over 2 is the same. S over root 10, that's the same. So this is the confidence interval for paired observations. Okay. Sorry. So if you just plug in the values, this is d bar plus minus t alpha over 2 s divided by root n. Okay. So it turns out that the mean demand, so this mean difference, which is mu1 minus mu2, well, you are 99%, you are sure that it's between minus 2,911 and 686, okay? So again, recall that hypothesis tests are equivalent to confidence intervals. So in the first question, we just test whether mu d, which was mu1 minus mu2, was equal to 0 or not, okay, in the first question, in the A part. So by just looking at this confidence interval, you can say that, well, this 0 is in the confidence interval. Hence, you can not reject the hypothesis because you are 99% sure that 0 is in this interval, right? Mu d is in this interval. Hence, this interval contains 0. So with 99%, you can say that mu d may be equal to 0. Right? So since the 0 is included in the interval, you cannot reject the hypothesis. But if I just ask you this, let's test this hypothesis. H0 mu1 minus mu2 is equal to, for example, 700 versus H1 mu1 minus mu2 is not equal to 700. Then when you just look at here, sorry, it's the element of the rejection region or the critical region, right? Hence, what you do is you just reject the hypothesis and say that, well, 1 minus mu2 is not equal to 700. Okay, so this is the table which is at the end of the book that is useful for testing the hypothesis for means. Please note that we do not cover this part. So in the next lecture, we will see that we have also alternative hypothesis which says mu can be smaller than or mu can be greater than. So, but for now, you can just look at this one. Mu is not equal to mu zero, right? So this table just gives a summary of testing hypothesis. So the first one says just test mu is equal to mu zero, sigma is known, this is the test statistic, this is the alternative, then this is the critical region, okay? And in the second part, again, test mu is equal to mu zero or not. Well, sigma is unknown, right? Hence, this is the test statistic that you use, the t statistic with b is equal to n minus 1 degrees of freedom. This was our alternative. For this alternative, this is our rejection or critical region. Okay. So, well, this is the difference of two means, difference of two means, difference of two means. Here you know sigma, here you don't know it, but you assume that they are equal. Here they are not known and you cannot assume that they are equal, or you do not assume that they are equal. Well, remember, so this is a tricky degrees of freedom. This degrees of freedom here is more easy if you are able to assume. So this assumption is a strong assumption. So if you are able to make this assumption, then calculating the degrees of freedom is very easy. If you cannot make this assumption, then you have a tedious formula for calculating the degrees of freedom. Okay, great. Then this is for the paired observation. As I said, later we will see that we have alternatives so that for example, mu1 minus mu2 is not always not equal to, but we will have hypothesis so that mu1 minus mu2 is smaller than d0 or greater than d0. And for the last part, for comparing means, we have some graphical methods, okay? So remember, we were talking about the box plots in the first lecture, okay? So this is the box plot for two different data where the amount of ascorbic acid in their blood. Okay, so there are 32 non-smokers. Well, this is the average of them. So this is the box. This is the average. This is what? This is Q1, right? This is Q1, and what this is Q2, right? And this is, remember, this is the max and this is the minimum. So by just looking at this, so again, this is Q3, sorry, this is Q3, this is Q3, this is Q1, and this is the quartile or the median, okay? And this is minimum and this maximum again. So what you do is you want to compare the means, right? So when you look at this, so this center, and this center, okay? Well, um, so without making a proper mathematical hypothesis test, you cannot say that, well, these two means are equal or not. But making visual plots are always good. So when you just look at this plot, you say that, well, this mean is very close to that one. Okay, so probably if you just make a hypothesis test, we will not be able to reject the hypothesis which says mu1 is equal to mu2. Okay, because when you look at the plot, it turns out that, well, they are very close to each other. Okay, but, well, this is another box plots for another type of data. I forgot the question, but So here, this is the first popular. This is the first sample, and this is the first sample. Okay, let's say this is sample one. This is sample one with no nitrogen, and this is sample two. Okay, with nitrogen, right? So what I will try to do is compare the means. So look at this one. This is the median of the first sample, and this is the median of the second. Okay. So when I just look at this, can you say that these two means are equal to each other? Well, that's a bit hard. Okay, so when you look at this one, you will probably say, well, the mean of the first one and the mean of the second one are different than each other. Okay, and um, and so a general rule of thumb, it's not, again, it's not for sure. It doesn't give the rigorous result that you found by using mathematical hypothesis test. But if quartile three, okay, is less than the first quartile of the other data, okay, so if quartile 3 is smaller than quartile 1 of the other data, then probably the means of two data are different than each other. Okay, so this is a general rule of thumb. But again, two important things. First one is visualizing the data. Making the plots is very good. You can see the data, you can understand what kind of things you are dealing with. But the second thing is that, well, you cannot directly say there is a difference between the means or not without making a proper mathematical hypothesis test. Okay, so this is the end for comparing two means. Let's meet in the let's say next video.